Yeah, I think we can skip the sponsorships for this podcast or whatever this is. All right, so let's talk about this point in particular. Are not all, I suppose, linear. So this may or may not come as a surprise to you. So first, let's recall what linear means.
It's closed under scalar multiplication and vector addition.
Yeah, so closed is weird here, because that's a subspace, right?
Yeah, like it doesn't leave its space.
Yeah, this is actually just a thing about functions. This isn't a thing about spaces. It's a good thought, though. Those same operations are coming into play. So, kind of thinking of a linear function, otherwise sometimes called a linear operator. I'm going to tend to use the word operator in this class, just because. Mostly that's because the idea of function in your head is probably stuck in the like algebra 2 f of x equals stuff, function notation. And these are just a little bit more kind of general. So, a linear function is a function where a of x plus y is ax plus ay. And I suppose I should be completely explicit with my parens here. Normally I would be saying x and y are vectors, right, and a is a matrix. That wouldn't be particularly interesting here because matrices are all linear functions. So, what's my other criteria? A of kx is ka of x. And these two things have to hold for all x's and y's in the domain of A. And scalars k. Guess with me? So, normally, right, I'm thinking of the domain of A as being some kind of vector space, so I'd have vector x, vector y. In this context, I'm kind of thinking about those, like, algebra 2 style functions.
If we're talking about just like straight lines, like the domain is already numbers.
Yeah, so in the case of the kind of, what am I talking about lines, right?
I wouldn't wrongly say that the parabola is linear.
Say again?
Like I wouldn't like wrongly say that like a parabola or like a square function is linear. Like if we're talking linear, I think it's straight lines.
Yeah, the word linear kind of implies something about straight lines, right? So you're like, okay, well, what are lines? Like, lines from an algebra 2 perspective are functions that look like f of x is mx plus b, right? So, an example of a line would be something like f of x is 3x plus 2. And we could check and see if this is linear, right? In order to check and see if this is linear, I could do f2x plus y, right? Okay, well if I do f to x plus y, I'm going to get 3x plus 3y plus 2. Oh. And what's the problem here?
You're gonna get two 2's.
Yeah, if I look at f of x plus f of y, I get 3x plus 2 plus 3y plus 2.
This
Huh. Those things aren't the same. Ergo, this line in particular is not linear.
you could probably generalize it by keeping it in just nx plus b, because you'd have with two b's.
Yeah, so if we wanted to generalize, right, we'd be like, okay, well, if we have f of x plus y, that's mx plus my plus b, right? And if I do f of x plus f of y, That's mx plus b plus my plus b. And if I need these two to be the same, right? Obviously I'm like, okay, well I've got an mx, I've got an my, but what would I need? Yeah, I need b to equal 2b, right? Okay, so to be linear,
I thought you were gonna write 2b or not 2b.
to be linear, 2b must equal b,
Therefore, 1 must equal
right? So to be linear, b has to be 0, yeah?
2. Mm-hmm.
Okay, so now I'm talking about functions like g of x are mx, right? So this is a separate family of functions. Are these all linear?
Yeah.
Are we sure?
Yes.
Yeah.
No. Because I checked the first property, right?
Yeah, you didn't check this.
By setting b equal to 0, I forced the first property to work. You guys see that? These have g of x plus y equals g of x plus g of y. So they pass the first part of linear function, but not necessarily the second. You guys see that? So I just have to do a quick check. So I'm like, okay, so let's do g to kx. That's m times kx. And if I do k times g of x, that's k times mx. Check. Okay, so linear functions, well, let's talk about lines. Which lines are linear functions now?
One's the post is
Good. Lines passing through the origin are linear. So, summary. Okay, now we're going to have one more question here. Because I still think there might be a weird caveat here. There might be a problem. If I'm drawing lines through the origin, right? I'm thinking like, okay, something like that. That's the case I just checked, right?
Yeah.
That's an M. Great, cool. What cases of M should I also be worried about?
negative m.
Yeah, I should probably worry about the case M equals 0, right?
Yeah.
So is the constantly 0 function linear? Well, this would be 0,
Yeah,
and both of these would be 0,
that would be 0. Yeah.
and this would be 0, and that would also be 0. Okay,
0
cool.
full.
So this includes the line y equals constantly 0. Ricky made this gesture. Yeah, is the one with undefined slope a linear function?
Well,
Hell if I know. It's expressed as x equals a constant, right?
yeah.
So it's not obvious to me that that's a function in any kind of reasonable sense. We might cock our heads at it and say, well, it's a constant function of y.
But then you're just like.
Yeah, I would ignore that case. So all the lines through 0, 0 are linear, so long as they're actually functions. You guys see that? And then what if it's not a line?
Like, what's the sign? Is that what you're asking?
Yeah, like just what if it's some other function? Like what's gonna be broken there?
Well, I'd imagine like the constant multiplication, because like if it's like x squared or some shit, you're gonna get like the square of your k.
Yeah, you guys see that? Any other function's gonna have a problem here because this is kind of these two together are kind of saying the range has to be a subspace. That's actually kind of where you were at earlier, Sid. Which is really good, right? Like, this is a little bit saying the range has to be a subspace, and the subspaces of R2 that are a function are all the lines through the origin. You guys with me on that? It's also a little bit like, what are the 1x1 matrices?
Scalars.
Yeah, the 1x1 matrices are scalars. We could rewrite these as M, the 1x1 matrix, times the 1x1 vector x.
Crazy.
Right, and then we'd be back in linear algebra land. And this would make a lot more sense, because obviously you can't add a vector. Right. That's going to give you something that's not got a column space that's a subspace. You see that? Okay, cool.